This is part 3 of our psychrometric chart introduction and working through the psychrometric chart. In this part, we're going to talk about the sensible heat ratio. But just a word of warning, if you have not watched parts 1 and 2 of this series yet, you are going to get totally lost as we go through this. So I would definitely suggest parts 1, 2 before you do part 3. We have a few things we have to talk about before we could talk about the sensible heat ratio. Number 1, what is sensible heat? Sensible heat is the heat of a substance you can measure. For example, if you have a room at 65 degrees, that's a temperature you can measure. If you have a room at 70 degrees, that's a temperature you can measure. The temperature difference between the two is a sensible heat gain or loss, depending on which way you're going. Sensible heat changes do not include any change of state, condensing or evaporating moisture. It is strictly a temperature that shows up on the thermometer. Total heat, or enthalpy, of a substance includes both the sensible heat and the latent heat. Latent heat is the heat you cannot measure with a thermometer. It's heat of condensation, vaporization. Okay, latent heat accompanies a change in state, liquid to vapor or vapor to liquid. Latent heat is a part of air conditioning because part of air conditioning we're dehumidifying. Latent heat happens in humidification as well. Happens anytime we take a single substance and either vaporize it or condense it. The third thing we do have to identify is we refer to a process line on the psychrometric chart. The process line on psychrometric chart is the line of cooling or heating. To find the process line, you plot the return wet bulb and dry bulb temperatures. You plot the supply wet bulb and dry bulb point, and you connect the 2 points with a straight line. That line is called the process line. That's what's happening in the system. Now let's use an example. I've shown this earlier. This is a digital output of the Testo Smart Probe application on cooling and heating loads. So when you look at this, you have a return air dry bulb temperature. We have a return air wet bulb temperature. We have a supply dry bulb temperature, and we have a supply wet bulb temperature. Now let's plot these on the psychrometric chart. Okay, in this case I'm going in using the carrier psychrometric chart. They're all the same, except some of them they're easier to read sometimes, so that's why we're doing it. Okay, so what we've done is my supply air is here. Okay, 74 point something. That's my blue arrow. Then we take our wet bulb, which is the red, and we come to the point where they cross. That is my plot point for my return air. We're cooling, so my supply air is 59 point something, dry bulb, and 56 point something wet bulb. Let's see what the point something is. Yeah, 59.1 and 56.2. Okay, where those 2 points cross is the plot point of my supply air. Now, if I draw a straight line between those 2 points, that's my process line. This becomes very important in a lot of the calculations we need to do when we're talking about the psychrometric chart. Okay, now just remember, okay, if we were talking BTUs per pound, you'd come up here and you'd be able to find that out. Okay, so we just have to remember we have other things we can do with this. Now, let's go ahead and move on. The sensible heat ratio is a relationship between the sensible heat load, that's the temperatures I can measure, to the total load in a process. It's a decimal. Okay, it's sometimes known as the sensible heat factor. It's the same thing. Sensible heat ratios range from 0.00 to 1.0. So we can do math on this, okay, to come up with an example, okay, just to show you. So the total cooling load in a system might be 48,000 BTUs. This is a 4-ton system. Is it actually running at 48,000 BTUs? We don't know that because we haven't calculated this yet. The sensible load, okay, based on things we've measured, is 38,400 BTUs. The latent load is 9,600 BTUs. So, sensible heat ratio is QS divided by QT. So we take our 38,400 BTUs divided by 48,400 BTUs. We have a sensible heat ratio of 0.80. This means that 80% of the load on the system is sensible heat. Now, as we talk about this, there's a rule of thumb for sensible heat ratios. Anything between 0.85 and 1.0 is computer rooms. Okay, computer rooms, for example, do not have people in them that often, so the latent heat load is very close to zero. Okay, people give off moisture as a part of your respiration. Electronics do not give off moisture, so it's a very dry environment. So very little of that load is latent heat. Comfort cooling, that's air conditioning, we want a sensible heat ratio of 0.65 to 0.80. The drier the environment, the higher the sensible heat ratio we can get away with. So if I'm trying to air condition out in someplace in New Mexico, Arizona, I can have a sensible heat ratio of 0.80 in most conditions. If I'm trying to air condition in Florida or the deep south on the East Coast, okay, I need a sensible heat ratio closer to 0.65 because I have to dehumidify. Now, for dehumidification, like a dehumidifier, and to purposely dehumidify, I want to have sensible heat ratios 0.50 to 0.60. Okay, because I want to pull as much moisture, latent heat, out of the system, out of the air as I'm cooling. The sensible heat ratio can also be determined graphically by the slope of the cooling process. A reference point of 80 degrees Fahrenheit at 50% relative humidity is used. A line is drawn parallel to the process line that passes through the reference point. Okay, and it then identifies the sensible heat ratio using the scale on the side. Let's go ahead and take a look at one of these. So our reference point in most psychrometric charts, if you look closely at the area of 80 degrees, dry bulb, and 50% relative humidity, you'll find a dot in the middle of the psychrometric chart. It's hard to see, but it is normally there. And if not, put one there on your chart. 80 and 50%. Okay, that's my reference point. My sensible heat ratios are up here on the side. Okay, that's my sensible heat factors. We draw a line through the reference point parallel to my process line. Okay, that hits one of these sensible heat, one of these numbers over here on the side. All sensible heat lines converge at the reference point. The ratio scale is over there on the right side, and you may find it off to the side sometimes on different charts. Every chart has it, but it's usually in different places. So, if we take a return air before cooling at 75 degrees, 50% humidity, supply air after cooling at 55, 90% humidity, okay, what we're going to do is we're going to plot the return air, we're going to plot the supply air, we're going to draw a straight line connecting the 2 points, that's my process line, and we're going to draw a line parallel to the process line that passes through the reference point. Then we're going to read the sensible heat ratio on the scale on the right of the chart. Okay, looking at the beginning of this plotted for the example that's with the PowerPoint, okay, this is not a real life condition. We have our return air, we're cooling through our supply air. We have our reference point. We draw a line that's parallel to the process line, but we extend it all the way over to my SHR or SHF scale. So in this case, this example, we're coming over here to a 0.83. Okay, sensible heat ratio 0.83. A lot easier than doing the math. So let's take a look at my example, the real life example that I pulled the other day from a system. Okay, 74.5 0.4, 65.9, 59.1, 56.2. Okay, those are the numbers we're going to be working with. So you may want to jot those down someplace so that you can follow through on another slide. And I'm going to just jot these down to the side just because the points are tough to remember sometimes. Now, do I know if the system is running correctly or not? Not yet. Okay, it's too early to tell if a system's running correctly. I'll come back to the slide in a minute and I'll tell you what's going on here. Okay, so we've plotted. My return error is here. We have our 74.4. That's my blue line. My red line is my 65.9. The point in the middle is my plot for my return error. My supply air temperature, 59.1, is my black line. My wet bulb return or supply air temperature is 56.2. Where the two meet is my point. The magenta or purple line that connects the two is my process line. Now, we take a line. My reference point is right there, 50% humidity, okay, 80 degrees. Right under that orange line, there is a big point. I'll show you this on my other chart in a minute. We take that line and we put it parallel to the process line through the point, and we extend it out. So this system has a sensible heat factor that's measured of 0.55. Okay, now, is that right or wrong? Well, let's take before I go into that, let me show you this other, where I actually plotted it, because I want to show you that little point that's in the middle there. Okay, if you look real close, and I'll try to blow this up a little bit. Okay, if you look real close at the 50 and 80, there is a point in there. So that's where I want my sensible heat line to go directly through. And then what we do, okay, is we come off over here to the right side, and it comes through the 0.55. Sort of makes sense? Okay, going back to the slide. Okay, is this right or wrong? In this case, okay, we had a 1.5 ton system. That's a 600 CFM system. Okay, 1800 BTUs per hour is what it should be. Now, we have an 18, when you calculate it all out, when it does the behind the scenes calculation, we are actually working at 18,138 BTUs per hour with a 10-year-old system. Now, I don't know about anything else in life, but air conditioning does not get more efficient as time goes on. Okay, air conditioning gets less efficient as dirt and everything builds up on a system. So what we actually have going on here is we are not moving enough air across this system. Okay, I have a supply air and return air, okay, 74.4 to 59.1, and I'm getting way off of topic here, but minus 59.1. Okay, that's a 15.3 temperature difference. Okay, this system is actually, there's a problem in the system, and I'm not going to go into it in this, but this is how you use all these numbers to troubleshoot a system. Okay, now, if you really want to do the math on this, you can do the math on this. Okay, now, I don't recommend it, but some people like doing things the hard way. So we have our supply air before cooling of 75 at 50, 55 at 90. Our sensible heat ratio is QS divided by QT. QS is sensible heat. Okay, sensible heat formula is 1.08 times the CFM, which is cubic feet per minute, times delta T. In this example, we're going to use, because we're talking about 1 cubic foot of static air, we're just going to use 1. QT, which includes latent heat, the formula is 4.5 times CFM times the change in enthalpy. So again, delta T, delta H, CFM. So the first thing we have to do is find our delta H. We have to find the change in enthalpy. Now, be aware the number shown here is actually reversed, okay, because we are actually removing BTUs per pound of air. So to find the enthalpy, again, you plot your two numbers, okay, and then your wet bulb line continues out, and that finds your enthalpy BTU per pound of dry air, okay? So in this case, my return air has an enthalpy of 28.2. My supply air has an enthalpy of 22.4. So I'm coming in with 28.2 and I'm coming out of 22.4 BTUs per pound. Okay, and I want to just give you a second to absolutely see that. So that's my delta H. So if we plug in our formulas, okay, and we put them here into something we can work with, my QS is 1.08 times CFM times delta T. My QT is 4.5 times CFM times delta H. So QS over QT is 1.08 times delta T divided by 4.5 times delta H. 1.08 times 20, because that's my delta T, divided by 4.5 times 5.8, okay, BTU per pound. We calculate those numbers out. We have 21.6 over 26.1, and we come up with 0.83. Now, I don't know about you going through this or going through this, which is easier. I think the plotting is a lot easier than the math, personally. So why is this all important? It all comes down to evaporator design. Okay, the evaporator coil is selected based on the application. If I have an application where I need a high SHR, like a computer room, or comfort cooling in a dry environment, air conditioning in a dry environment, or sometimes even refrigeration, because we don't do a lot of dehumidification in refrigeration. Okay, we want a high SHR. If I want a low SHR, in other words, lots of latent cooling along with the sensible, I need to have an evaporator with more rows, and I'll show you a picture of what I'm talking about in a minute. Evaporator coils with more rows are thicker coils than coils with fewer rows. Thicker coils increase the amount of time the air stays in contact with the coil. Thicker coils result in increased dehumidification. The longer the air stays on the coil, the more it's going to dehumidify. Think about the cold glass in a humid environment sitting on a counter. The longer that cold glass stays on that counter, the more moisture comes up on the side of it, and the more moisture falls onto the counter. If I just leave that glass there for a short period of time, drink the water or Coke that's in there, and get it out of there off the counter, I'm going to have very little moisture on the counter. So the longer the air stays in contact with cold, the more dehumidification that happens. So if we take a look at the side of a coil, this is what I'm talking about. The thinner the coil, by rows, I mean how many rows that way, not this way. The less dehumidification, higher SHR. The thicker the coil, the more dehumidification, the lower the SHR. In other words, the more latent heat. So between these two coils, this is going to be great in an area where I don't need a lot of dehumidification. This has to happen in an area where I have a ton of dehumidification. More efficient systems use larger coils. By larger coils, do not affect the sensible heat ratio of a system. thicker coils do affect the sensible heat ratio of the system. Thicker coils lower the SHR of a system. Okay, and that's basically takes care of SHR. We're going to move on to apparatus dew point in part 4.